Today we're going to talk about labeled combinatorial structures, which we use exponential generating functions to analyze. Again, we're going to have a set of combinatorial constructions that we can use both to specify the structures and to immediately transfer to equations on generating functions. This is in the overview, this is the second lecture on analytic combinatorics on the symbolic method. And again, we're going to follow the same general approach that we did for unlabeled structures and ordinary generating functions, where we have a specification that's automatically turned into a generating function equation. And then later in the second half of the course, we'll talk about turning those generating function equations into the asymptotic estimates that we're looking for. Now, I want to give the same warning that I gave at the beginning of the last lecture. Quite a bit of this lecture is a quick review of material that we went through in much more detail in part one of the analytic combinatorics course. So one consequence of that is this lecture is a little bit longer than usual. If you took analytic combinatorics part one and are bored because you understand everything, that's great. Just fast forward through. There's some new material on labeled trees, and then do the exercises, or use this as an opportunity to review the material. If you're starting with this course and you find that things are moving too fast, you can always go and see some details and motivating applications in the earlier course. Okay, so let's talk about the basics of labeled structures. So the idea is that objects in labeled combinatorial classes are composed of atoms, and if there's n atoms, they're labeled with the integers 1 through n. So for unlabeled objects, there had to be a difference in structure for the objects to be different. For labeled objects, we add the extra constraint that it's the way that they're labeled makes for different objects. So these are two different labeled objects because the labels go in different order around the square. You can't transform one into the other. Or these are different labeled objects because the one without degree 3 has got a different label in each of the cases. So there's many more possibilities for labeled objects, and as we'll see, that's why we use exponential generating functions instead of ordinary generating functions. So here's an example, cycles of labeled atoms. How many cycles of labeled atoms are there? Well, you make a cycle, so here's a cycle of 4 labeled atoms, and you fix one item, say the 4, then you have all permutations of the remaining n-1 items make a different labeled object. So it's easy to see that the number of different cycles of labeled atoms is n-1 factorial. But then we can look at a more complicated example. How many unordered pairs of labeled cycles of size n are there? So there's 3 different unordered pairs of labeled cycles of size n. You got one, so it's a pair, so one of them has one object and the other one has 2. You can pick one of the 3 labels for the one that has one object, and then there's only one way to label the one that has 2 objects. So there's a total of 3 different unordered pairs of labeled cycles of size n. For 4, there's 11 different. You can pick you can have 1 and 3, and you can label the one object any one of the 4 ways. But then the cycle that has 3 objects can be in either orientation. It could be 2, 3, 4 or 2, 4, 3 on the top example. So that makes 8, or you could have a pair of cycles of size 2 each. And then there's 3 different ways to label them, essentially by choosing out of the 4 the 3 different possibilities. And remember, it's an unordered pair, so 1, 2 on the left and 3, 4 on the right is the same object as 3, 4 on the left, 1, 2 on the right. So that's 11 for 4, and how many for 5? And the answer to that turns out to be the Stirling numbers of the second kind. And we'll talk about that probably in the next lecture. Okay, so Here's the basic definitions that we're going to work with, and these correspond precisely to the basic definitions that we used for unlabeled classes. So first, we say a set of n items is said to be labeled if they can be distinguished from one another, and without any loss of generality, we use the labels 1 to n to refer to the atoms. So a labeled combinatorial class is a set of objects built from labeled atoms, and also there's an associated size function. Again, just as before with unlabeled classes. So we use exponential generating functions that we associate with labeled classes, and that's just a formal power series. We use a variable z, the function a of z. It's the sum over all objects that belong to the class, z to the size of the object divided by the size of the object factorial. That's what makes it an exponential generating function. And just as with unlabeled classes, we have the fundamental identity that's elementary, that you can express the generating function as the sum from n bigger than 0, an, the number of object of size n, z to the n over n factorial. And that's elementary because we just collect terms, all the objects of size n. There's a sub n terms of size n, and that's then an identity for the generating function. And that means that if we know the generating function a of z, and we want to know the number of objects of size n, we just find the coefficient of z to the n in a of z and multiply by n factorial. That'll be our goal later on. For right now, we're going to talk about how to build combinatorial classes and how those constructions lead us to equations that the generating function must satisfy. With the symbolic method, just as for unlabeled classes, we specify the class and at the same time characterize the exponential generating function. So let's look at some basic labeled classes. So one is called an urn. That's just a set of labeled atoms. The order doesn't matter. There's actually only one urn of each size because the label doesn't matter. It's just a set of atoms. So that means the counting sequence, the number of urns of size n, is just 1. And what's the exponential generating function? It's just sum of z to the n over n factorial times 1. That's just e to the z. That's a basic labeled class. The urns, the exponential generating function is e to the z. Permutations, that's another familiar labeled class. A permutation is a sequence of labeled atoms. And here's the familiar, there's 24 permutations of size 4. So the counting sequence, the number of permutations of size n, is just n factorial. What's the exponential generating function? It's just 1 over 1 minus z. The sum, n bigger than 0, n factorial is the counting sequence times z to the n over n factorial, because it's exponential generating function. That's just the sum of z to the n, and that's 1 over 1 minus z. That's a second basic example of a labeled class. And the third one is the one that I introduced at the beginning. It's a cycle. A cycle is a cyclic sequence of labeled atoms. There's n minus 1 factorial cycles of size n. So what's the exponential generating function? It's sum n minus 1 factorial, z to the n over n factorial. That's sum of z to the n over n, or log of 1 over 1 minus z. So those are three basic labeled classes, and they actually serve as the foundation of the combinatorial constructions that we're going to consider. Now, the operations that we perform on labeled classes in order to create combinatorial constructions are based on this operation, the product operation. We had a product operation for unlabeled classes, which was the Cartesian product, where we take one item from each class to make a pair. This operation, called the star product operation for labeled classes, is the analog to the Cartesian product. So given two labeled combinatorial classes A and B, their star product, or labeled product, is a set of ordered pairs of copies of objects, one from A, one from B, but they need to be relabeled in all consistent ways. And here's a very small example. If we have a class that consists of a single 2-cycle and another class that consists of a single 3-cycle, and we take the star product, we get a class that consists of 10 pairs of objects. We have the 2-cycle and the 3-cycle, but we need to relabel them in all consistent ways. We want to use the labels 1 through 5, and we have to make sure in the 3-cycle that we maintain the orientation 1 to 2 to 3, smallest to middle to largest. So for example, on the left, it shows all the ways to assign 1 to the 2-cycle. It can be with 2, 3, or 4. And then what's left over gets assigned to the 3-cycle, but in the order, smallest, middle, largest, as we go clockwise around the cycle. And then next is the 2 cycles with 2 without 1. There's 3 of those with 3, 4, and 5. And again, the ones that left over, the labels that get left over, get assigned to the 3-cycle in the order smallest, middle, largest as we go around clockwise. And then there's 3, 4, and 3, 5. And again, just 2 possibilities. And then finally 4, 5 with 1, 2, 3. So that's the star product, example of the star product for simple labeled classes. As you can see, the possibility multiplies, but this, as you'll see, is a perfect analog to Cartesian product that lets us build up labeled combinatorial classes of remarkable richness and complexity. For example, again, to use a familiar example, you can create permutations just by taking star products of atoms. So a single the permutation of size 1, there's only one, it's just an atom labeled 1. If you take the star product of 2 atoms, all you can do is label the first one 1, in which case the second one has to be labeled 2, or we can label the first one 2, in which case the second one has to be labeled 1. That's Z star Z, that's the permutations of 2 elements. For each one of those, if you take the star product again with another Z, then there's 3 possibilities, essentially labeling the first item either 1, 2, or 3, and then labeling the next 2 items has to be a sequence. So in all consistent ways, just put the next 2, the labels that are left over in order. So that's the first 3, and then the second 3 are what you get in the star product of 1 and 2, 1. It's again, first one can be labeled 1, 2, 3, and the others are labeled in reverse order. And then, for example, the second permutation in that list, 2, 1, 3, if we star product that with another Z, then we get 1, 2, 3, 4, and then the remaining labels go in the order, middle, smallest, largest, and then we get 4 possibilities. For each one, we get 4 possibilities. So that's a way to specify the set of permutations using the star product operation. And just as with unlabeled classes, we can write A squared for A star A cubed for A star A, and so forth. And that's a simple example of a combinatorial construction. We say that the permutations of length n are Z to the nth. And we're going to next look at many other examples of combinatorial constructions. But that's the basic operations for constructing labeled classes.